In this video, we will solve 10 problems involving simple and compound interest. In the first problem, we are asked, Joshua's investment has grown to 56,000 in 2 months and 56 days. If the rate was 6% compounded monthly, what was the investment amount? So in this problem, we have the rate which is compounded monthly, and we don't know the investment amount. In other words, we don't know the present value. I'll quickly remind that the formula for present value under compound rates is future value times 1 plus I exponent minus n. So here I is the periodic rate. It's a nominal rate divided by the number of periods per year, and n is the number of periods per year times number of years. So let's substitute amounts here into this formula. So present value is 56,000, 1 plus I, which is the periodic rate. It's 0.06 divided by 12 because we have 12 months in a year. So then following this formula here, n equals to m times t. So m in this case is 12 times number of years. Now we need to convert 2 months and 56 days into years. So in brackets we'll write 2 over 12 plus 56 over 365, assuming that there are 365 days in a year, and that's what we assume when we're not given exact dates. Now we also need to put negative sign here. Let's solve this. 54,937.38 rounded to 2 decimals. Here is the solution to this problem. Let me erase this auxiliary formula so that you can see this solution unobstructed. Now let's proceed to another problem. How much time in years and months is necessary for an amount to double at 4% compounded quarterly? We are looking here for the n. So we need the formula for n. Now let's remind ourselves how to get that formula. So future value is present value 1 plus I exponent n. So we can do future value divided by present value equals to 1 plus I exponent n. So from here we can find logarithms. Future value divided by present value equals to n times logarithm 1 plus I. From here we easily get the formula for n, which is logarithm future value divided by present value divided by logarithm 1 plus I. And basically that's the formula we are going to use to solve this problem. Now if we proceed to the actual solution of the problem, we see that n equals to logarithm. Future value is 2 present values, right? So each dollar becomes $2. In other words, 2 over 1. So future value becomes 2, present value is 1. If we take this for each dollar, and logarithm 1 plus I is the rate compounded quarterly, which is 0.04 divided by 4. Because we need to find periodic rate, and there are 4 quarters in a year. Now let's compute that. 69.66071,689. I'm being precise right now because I'm not done yet in this solution. So we have 69.66 quarters because the rate is compounded quarterly. So I'll write here quarters. Now we need to convert quarters into years and months. So dividing by 4, I see that it's 17.41517922 years, which is of course 17 years, and then 4.98 months. I simply took 415,17922 and multiplied by 12 in order to find month. But rounded to the next month, we have 17 years and 5 months. And this will be the solution to this problem. 17 years and 5 months. Now let's consider another problem. Kamila invested 4,500 for 6 years. For the first 2 years, the amount grew at 6% compounded semi-annually, and for the remaining 4 years, the amount grew at 5% compounded daily. What was the accumulated value at the end of 6 years? What was the interest earned over 6 years? So, of course, we will start with the same formula, which is future value equals to present value 1 plus IN. And here we will notice that 4,500 is the present value, so we'll have future value 4,500 times 1 plus 0.06 divided by 2, because the rate is compounded semi-annually. Exponent will be 2 times 2, right? So it's 2 years for the first part of this investment. Now, whatever that becomes to will continue to grow at 0.05 divided by 365 times 4, because there are 4 years remaining in this investment. Now we will compute this. 6,186.06 if rounded to 2 decimals. Of course, interest is future value minus present value. So 6,186.06 minus 4,500, the amount which was invested. 1,686.06. Here we go. So that's interest, and that's the future value for this problem. The next problem is asking us, what nominal rate compounded semi-annually is necessary for 4,500 to earn the interest amount of at least $720 in 2 years? Again, we can remind ourselves how the formula for interest rate will look like. So that's our main formula. From here, we will derive the formula for I. We'll just find exponent, future value divided by present value, 1 over n equals to 1 plus I. From here we have I, which is future value divided by present value, 1 over n minus 1. And that's the formula for periodic rate that we will be using to solve this problem. So here we substitute values into this formula. So future value is 4,500 plus 720, that's the future value because you take the present value plus the interest earned divided by 4,500. Total number 1 over total number of periods. So the rate is compounded semi-annually for 2 years. So we have 2 times 2 because we have in total 4 semi-annual periods in 2 years minus 1. I equals to 0.037801986. Of course, that's periodic rate or rate per 6 months. That's because each period here is half year, 6 months. So now J, which is the nominal rate, is this periodic rate times 2, 0.0756. In other words, 7.56% compounded semi-annually. And that will be the answer we're looking for. What rate will give a higher future value in 6 months? A simple rate, 10% PA, or 10% compounded annually? Give an example to demonstrate. Well, let's remind ourselves the future value for simple rates. Simple future value is principal 1 plus R T, where R is the rate per year and T is the number of years. And of course, for compound rate, the future value formula is present value 1 plus I n. So let's solve this problem right now. So for A, let's take amount of $1,000. It doesn't matter what amount we take actually to demonstrate which rate will give higher future value, but we'll take $1,000 for convenience. 1 plus 0.1 times 6 over 12. So the rate per year is 10% here, and the number of years is 0.5 or 6 over 12. That's, of course, 1050. B is 1000, 1 plus 0.1, and here we have to take exponent 0.5, which is also half year. 1048.81. This is an interesting example because it shows that actually investing with simple rate is sometimes better than investing with compound rate. You can see that the answer to this question is that if you invest for 6 months, that is to say for the amount of time which is not enough for the rate to begin the compounding process. So this 6 month here is less than 1 year, and the compounding period here is 1 year. So in this case, simple rate will give you a higher future value than the compound rate. Of course, if you invest under compound rates for the amount of time which surpasses the compounding frequency, so in this case, if you invested for amount of time which is longer than 1 year, in this case, you of course would result in higher future value for the compound rate. Let's now proceed to the next problem. What nominal rate compounded quarterly is equivalent to 7% compounded daily? We can compare investment of $1 under both rates. So let's invest $1 at some rate compounded quarterly. So $1 is going to be present value, 1 plus I. This is the rate we don't know, but we know it's compounded quarterly. So after 1 year, the exponent will be 4 here, right? Because there are 4 quarters in a year. And that should be equal to $1 invested at 0.07 divided by 365 for 365, right? So this is $1 invested at 7% compounded daily for 1 year, because there are 365 days here. So if we simplify this, of course, we can remove $1 because it doesn't change any equation here. But from this equation, we can simply find I. And this is so we divide both exponents by 4 here, minus 1. 0.017652315. What we found is, of course, a rate per quarter. There are 4 quarters in a year, so in order to find the nominal rate j, we will need to multiply I by 4. And we will obtain, it's going to be 7.06% compounded quarterly, rounded to 2 decimals. And this appears to be the answer to this problem. By the way, we solved this problem without using any formula. We simply compared $1 investment over 1 year. For compound rates, if rates are equivalent over 1 year, they are equivalent for any amount of time. But we, of course, can have a formula, which is I2 equals to 1 plus I. So this I is the known periodic rate, and this I2 is the one we're looking for. M1 divided by M2 minus 1. I can just put 1 here. So I1 is going to be the known periodic rate. M1 is going to be the compounding frequency for the known periodic rate, and M2 is going to be the compounding frequency for the rate we're looking for. So if we use this formula, we can be right away here, and we can solve the problem the same way. Next problem is this. The investment of $5,000 provided $400 of interest in 1.5 years. The interest rate was compounded monthly. If this investment is continued at the same rate, how much more time in years and days will it take to earn another $400 of interest? Well, again, we already know the formula for I, and that's future value divided by present value, 1 divided by n minus 1. So we'll use this formula to find a rate for the first part of this problem. In this problem, we don't know the rate in order to answer the question, but the first part of this problem gives us information to find the rate. So this formula gives us that I equals to 5,400, because it's 5,000 investment and $400 interest, which gives the future value of 5,400, divided by 5,000, and 1 over 12 times 1.5, because n equals to m times t. M is the number of times the rate is compounded, in this case 12 times per year, because the rate is compounded monthly, and there are 1.5 years here, minus 1. So let's compute that rate. 0.004284767. We're not going to round this rate for now. We'll just keep it in memory of the calculator and proceed to the next part of the problem. In the next part of the problem, we need to find time. So we'll use the formula for n. It's going to be logarithm, future value divided by present value, divided by logarithm 1 plus I. Again, here logarithm, future value is going to be, now we are going to earn another $400 of interest, so it's going to be 5,800, because now we deal with another present value which has become 5,400, divided by 5,400, which is the new present value for the second part of this problem, and logarithm 1 plus I. And I is this I that we already have found. So let's now see what the answer is. 16.71314,905. And what is this? We found that it's 16.71 months. Let's convert that to years. It's 1 year and 143.36 days. Rounded to the next day, it's going to be 1 year and 144 days. Usually in problems like this, we round to the next period, the next day in this case, because the problem is asking us in years and days. In our next problem, we're asked the following. Banks A and B offer 3% compounded monthly and 2.9% compounded daily, respectively. Which bank offers a better rate for investments? Use effective rate to compare the banks. What we need to do, we need to take 3% compounded monthly and convert it to effective rate. And the same we should do with 2.9% compounded daily. We also will convert it to effective rate. How do we convert to effective rate? First of all, we remember that effective rate is defined in our course as a rate compounded annually. Well, we can remind ourselves how we can find that. So we invest $1 at some rate compounded annually. So 1 plus f. Let's f denote that rate compounded annually. And that should be equal to 1 plus 0.03 divided by 12. And 12 will be the exponent here. Now what this means again is that $1 has been invested at some unknown effective rate, and because it's the rate compounded annually, so there is no exponent here, or more correct, there is an exponent which is exponent to 1. But we don't have to write that exponent because it doesn't change anything. And on the right side, we have $1 invested at 3% compounded monthly for a year. And they should coincide because we need to find effective rate, which is equivalent to 3% compounded monthly in this case. So from here we find f, which is 1 plus 0.03 divided by 12. exponent 12 minus 1. F is going to be so this F is the rate equivalent to 3% compounded monthly. Let's just use 1 here, F1, to differentiate it from another effective rate that we'll now find for 2.9% compounded daily. So we'll do the same thing. F2 will be 1 plus, now this time it's going to be 0.029 divided by 365 because there are 365 days. 365 minus 1. So F2 is going to be 0.029423409. Well, for investments, which one is better? F1 or F2? Of course, you will get better future values with higher effective rate. So that will be the solution of our problem. F1 is better, which means that 3% compounded monthly is better than 2.9% compounded daily. And we have shown it using effective rates. The next problem is this. What annual simple rate is equivalent to 9% compounded daily over the term of 250 days? When you compare compound rate to another compound rate, it's always enough to compare those rates for the period of 1 year to find equivalent rate. When we compare compound rate to a simple rate, it's not the case. Time period or the term is very important in this comparison. So what we'll do, we'll find future value of $1 invested at 9% compounded daily for 250 days. And that should be equal to 1 plus some simple rate, which we don't know, which also is invested for 250 days. Now we need to solve this equation for R. Well, in order to solve this equation, we'll just simply write that that's just a simple algebra here to solve this equation, and we now solve it in a calculator. 9.28% rounded to 2 decimals. So that's the answer. 9.28% simple rate is equivalent to 9% compounded daily over 250 days. Now we will proceed to the next problem. On January 29, 2021, $10,000 was split and invested into 2 accounts. $3,000 was invested at 4% PA and $7,000 was invested at 6% CA, which is compounded annually. What was the resulting value of this $10,000 investment on November 7, 2021? What was the effective rate realized for this investment? First and foremost, we need to identify how many days is between these 2 dates. So the investment was on January 29, 2021, and it matured on November 7, 2021. The day of the investment is considered to be day 0. We can find the number of days in the following way using Excel, for example. $282 days. Now, this $10,000 was split. Let's find future value of $3,000 first. So simple future value is going to be 3,000, 1 plus 0.04 times 282 divided by 365. 3092.712329. What about the second part of the investment, which is 7,000? That was invested at compounded rate, so we'll use compound rate future value. And this results in $7,000, which grows at 6% compounded annually, so 0.06. And because it's compounded annually, so it's going to be exponent for the number of years, which should be taken from 282 days. 282 divided by 365. So that's going to be our exponent. 7,322.332078. Of course, I keep this value and this value in a calculator to find the total value for this investment. So S plus future value becomes 10,415.04441. But we're not done yet, because we need to find the effective rate realized for this investment now. How do we find that effective rate? Well, $10,000 grows at some effective rate. It's $10,000 grows at some effective rate for 282 days, right? So 282 divided by 365 in order to become 10,415.04. We can round here, because round to two decimals, because that's the actual amount which will be picked up from the bank. You cannot pick up more than cents from the bank. So from this equation we need to find f. 1 plus f exponent 282 divided by 365 will equal to 10,415.04 divided by 10,000. From here, we'll be solving this equation. We need to get to f. On both sides, we'll take exponent reciprocal to this exponent here. We'll obtain that f is equal to 10,415.04 divided by 10,000. Exponent will be reciprocal, so 365 divided by 282 minus 1, because there is 1 here. So this gives us f 5.40% if rounded to two decimals. That's the effective rate which we had to find for this problem. Of course, this effective rate can also be found with a formula if someone wants to bypass algebra. Effective rate is future value divided by present value, 1 over n minus 1. This is actually a familiar formula for finding rate. It's just in this case, effective rate is nominal rate and periodic rate simultaneously. Before we had this formula for periodic rate for I, but because for effective rate the period is 1 year, periodic rate and nominal rate are the same for effective rate. If one uses this formula, then bypassing algebra, it is possible to be right here and then finding the answer, which is 5.4% compounded annually. That finalizes our 10 problems for this class. Thank you for your attention, and bye for now.